Good morning all of you. Myself Dr. Harale, Assistant Professor, Department of Physics, S.G.M College, Harale. I am going to discuss a second part of my lecture series, Nanoscience and Technology Introductory part. In last lecture we have seen some basic concepts regarding the nanoscience and technology. So we have just overlooked the concepts regarding the nanoscience and technology. So what we have learned up to now, what is meant by nano, scale, what is the scale for nano? 1 nanometer is equal to 10 raised to minus 9 meter. The general scale. Regarding basic information about nano, who is the nano visionary? We have already discussed regarding the research Feynman, who give the concept of nanotechnology. What is meant by technology and what is meant by nanotechnology? Now, then revolutionary technologies waves. What are the different technology evolved with respect to years, and what is the role of nanoscience and technology in the evolution of different technologies? Scale game. The scale things like nanometer to meter and more. That another one is relative sizes and the detection. How we can detect the nanomaterials by using different devices. In the range, size range, we can detect by using a human eye. For the laser side, we have to go for optical microscope, and then we have to go for the detection of that smaller objects by using electron microscope. And scaling down to the nanometric scale. When you compare with the bulk material, you have to go for meter scale to nanometric scale. This part we have already discussed regarding this our earlier lecture. Now, just here we have seen the what is nano and related to that term nano, 10 raised to minus 9 or 1 billionth of that. So 1 nanometer is equal to 10 raised to minus 9 meter. Now, what is the nano system? Suppose they consider a block of metal having the coordinates x, y, z coordinates is a 3D box having the 3 coordinates x, y, and z is a dimension, a block of metal. So basically it's an insulating metal, insulating box. Now, if you cut the one single dimension and make it a thin film, you will find that this three-dimensional structure changes into two-dimensional. Okay, so this one is a 3D. Now when you cut down the axis, like this one axis, z axis, so it has only a 2 dimensions, only 1 dimension we have taken down in the range of 1 to 10 nanometer, which is called as ultra thin film. So this type of material we can call as 2D material as compared to 3D. Here 3 axes, x, y, and z. Now if you cut down the 1 dimension, then the object becomes a 2-dimensional, and a 3rd dimension is very small in the range of 1 to 100 nanometers. So this is called as 2D material. Now again, when you cut down more, another 1 dimension, that is the only 1 dimension is present there, and other 2 dimensions are very small, which is called as 1-dimensional material. These are the 3 different forms of that nano system: 3-dimensional, 2-dimensional, 1-dimensional. Now, what in each case, when you reduce the dimensions, then it changes from 3D to 2D, 2D to 1D. Now, if you construct all the dimension 3-dimensional, then you will find the cluster of nanoparticle, which is called as 0D. This is the distinguish between the 3D materials, 2D materials, 1D materials, and 0-dimensional. Like for example, a quantum dot. This is just example of that 0-dimensional materials. 3D cube, ultra thin films like a thin films is involving this 2-dimensional materials like nano sheets, for example. Now, what is the example for a 1-dimensional material is nano rod or nano tube. Example for that 0-dimensional is just quantum dot. That's why missing the dimensions falls in the quantum region. So this includes this 0-dimensional. The quantum mechanics comes in the picture. At least one of its properties is size dependent. When you change its size on the x-axis or y-axis or any axis, when you reduce any dimension, then at least one of its dimension is in the form of nano, then you can call as its nano materials. So what happens with that nano materials? The metal block is initially insulating. When this block is get converted into nano rod, it may be conducting. So that's a extra evolution of properties occurs due to this nano dimensions. Now, how we compare with that nano and bulk? In earlier days, the computer, normal computer, having the various occupying the large space to compute this functioning of its computer. Now we can put a small device like tablet in our hand, so size reduction possible due to miniaturization of that electronic all the component parts. That's why the size reduction happens. Then you will find out the device of final device having a dimension is very smaller dimension. Now why this happening? A shared computer, thousands of people sharing a mainframe of computer in earlier days. Now in present personal computer we can handle by using the personal hands. So this is a revolutionary happens, and why this happens? Due to miniaturization of size. Size reduces and its functioning and other properties enhances. So you can minimize this size and you can make devices which is called as nano devices. So, but to visualize this size effect, just consider a normal example like human hair, having the diameter around 100 micrometer. When you check this human hair under the microscope, electron microscope, you will find this image having the dimension 20 micrometers. This one is scale by 20 micron. Now carefully observe this sheet or layer structure. You can observe under the electron microscope. You will find out this some layered structure, overlapping structure observed in it. Now you can cut this hair into different slices. So these are this 100 slices of that human hair. Now consider only one slice of that out of 100, one slice. Then dimension having the 1 micron only, a diameter, consider this 1 micron. Then again you take these slices, 100 slices, 1000 slices. Here 100, here is 1000 slices. Again take one single slice. So this one is a single slice having the dimension D is equal to 1 nanometer. So we have started with 100 micron up to 1 nanometer. This is a journey of that human hair. When you cut down, make a slice, then you will find the diameter actually, the width or thickness of that slice in the range of 1 nanometer in just a single thread. This is a schematic representation cutting down the cross section of human hair. Now what happens when you cut this size? What parameter changes with respect to that changing this size or cutting that material to a very smaller part? One of the general questions, or how we can compare with that nano size material. A small is a nanometric. Here are some interesting answers. Now by using that points or sentence, we can analyze what is nano and how we can generally realize what is nano. The diameter of C60 is called as a buckyball molecule 660, generally known as full ring. So diameter of that is in the range of nano. Another one is half as a white as a DNA molecule. We can take a DNA molecule, then half of that in the range of nano. 2 times the diameter of rubidium atom, approximately nanometer, 1 nanometer or something. 10 times the diameter of hydrogen atom. We can consider the 10 times diameter of the hydrogen atom is equal to approximately 1 nanometer. The de Broglie wavelength of an electron with an energy which is related to approximately a nanometric scale. How much your fingernail grows each second, which is in the 1 nanometer per each second. How much the Himalayas rise in every 6.3 seconds, which is also approximately 1 second. The thickness of a drop of water spread over a square meter, like that size, in range of nano. Now scaling, we have already discussed regarding scaling from meter scale to nanometric scale. Now consider this scaling up from nanometer. That is starting with a smaller atom or molecule and comparing with the largest objects. So here water molecule which measures the approximately 0.5 nanometer, here water molecule 0.5 nanometer, just 0.5 nanometer, 50 angstrom, is about as a big relation to an apple as an apple is to planet Earth. You can consider here is a starting point, which is a water molecule, and it is then changing with the size. Here is the apple and here is the Earth. So starting with small molecule and comparing with the highest object, it's a long way down to the nanoscale. So we have to go from this to atomic or molecular scale. Now, to better understand regarding the nanoscience and nano related concept, we consider just generic some points related to this carbon atom. So new number of carbon atoms variation with respect to nanoscale. What happens with that carbon atom when you go at nanoscale? Bohr radius, consider Bohr radius in the range of 0.05 nanometer. Now consider carbon atom, that's van der Waals radius is around 0.17 nanometer. In 1 nanometer line, how much situated the carbon atoms is 3 carbon atoms. In 1 nanometer into 1 nanometer, 1 by 1 surface. So how much? 3 into 3 is a 9 carbon atoms can situated. Now consider a 1 nanometer cubic. So 1 nanometer into 1 nanometer cubic. So how much? 9 into again 3, 27 carbon atoms. So what this represents that in 1 nanometric cube we can situate it 27 carbon atoms. Again consider the 100 nanometer scale, 100 nanometric cube, 100 nanometer, 100 nanometer, 100 nanometer. So you can place 2.7 into 10 raised to 7 carbon atoms. So this is the beauty of that nanometric scale, how you can place this atoms at the nanometric scale. So this is a schematic representation for this carbon. This green color indicates the electron, these are the protons and these are the neutrons. 6 proton and 6 neutrons are present in the carbon atom, this general structure of carbon. So these are the relation with that nanoscale as compared with that carbon atom. Now when you consider the particle size and the number of atoms in that particle, how much atoms are involved to form that particular grain. So D is the particle grain size or particle size D, and here is the number of atom in a particle or any grain, how much these are present. So starting from here 10 micrometer to 100 picometer, here is the nanometric scale. So you can find out the atom and 2-3 atoms molecules together which form the 2 to 3 atoms present in that particle. When you go for molecular cluster like full ring, so involvement of number of atoms 20 to 70. Like that metallic cluster, nanocrystalline material, semiconductor material, when you go upwards, then the particle size increases along with this, and also in meanwhile the number of atoms present in that material also increases. So what is that relation? You can find out by using this table. This table shows the example of material system on the size scale. So here is the size, different size. Here is scientific notation for that. Example, for the comparison we have taken one example, and observation, how you can observe these objects or particles or examples. So here is the scale 1.7, this is a metric scale. So notation 1.7 into 10 raised to 0 is like human height. You can compare. You can observe this by using a naked human eye. Like that 1 centimeter wedding ring, 1 mm thickness of CD. Compact this. You can observe this one object by using human eye. Also you can observe the thickness of CD by using optical microscope. Also by human. 100 micrometer. When you consider the scale of 100 micrometer, so 1 into 10 raised to minus 4, a plant cell. The size of that plant cell is around 10 to 100 micrometers. So you can see the 100 micrometer object by using human eye, using optical microscope. Also you can see some parts, components of that cell by using electron microscope. Also a laser than 100 micrometers, 10 micrometer consider the animal cells you can find see in optical microscope as well as electron microscope. Now below that 1 micrometer, the bacterial cells, some bacterial cells having the size less than 1 micrometer, you have to use the optical microscope or electron microscope. You cannot see directly by using human eye. So below that 100 nanometer scale, some viruses having the size in the range of 100 nanometers. So these viruses you have to use the tool to observe these viruses electron microscope. Below that again 10 nanometer, some also various viruses, protein molecules are present involved in this range of 10 nanometers. So also you have to use electron microscope to observe this particular viruses or protein molecules. Below that size, up to now we have checked up to 10 nanometer. Below that 1 nanometer, consider the nanometric scale 1 nanometer, 1 into 10 to minus 9. So some protein molecules, the size of protein molecules in the range of 1 nanometer, aspirin molecules size in the range of 1 nanometer. You cannot go with the optical microscope, you have to use the electron microscope for that to see this particular protein molecule or aspirin molecule. So how we can relate with this our particular normal day-to-day life example. So human fingernail grows 1 nanometer every second. So we can realize the nanometric scale by using this example. Also similar man's beard grows 5 nanometer every second. So each second the length of that hair increases with 5 nanometer. So these are the two local examples, day-to-day life examples, and this we are not focusing on that. But when you see carefully 1 nanometric scale for each second, that's why we can find out after some days the nails grown with some particular size. Also, you will find out some increase in the length after some days. You cannot identify by each and every second. So, but they are growing with per second 1 nanometric scale in case of fingernail, 5 nanometer in case of hair. Now, why it is necessary to know about the nanoscience? We are talking about nanoscience, nanotechnology, nanotechnology. We have to use here, we have to use there, nanotechnology. But what particularly we have to know about the nanoscience? So every assembly in the nature is made an atom by atom approach. Every natural occurring assembly, molecular assembly in nature made up of atom by atom. Some atoms come together which form some molecule, and molecule comes together which form a cluster, and then cluster forms a particular bigger size object or grain. Then by using that grain which forms a particular materials which we call as some nanomaterials, if it is in the range of 1 to 100 nanometer, or beyond that some micrometric scale, then we call as just bulk materials. These synthetic routes are to synthesize this nanomaterials. The synthetic routes are most energy efficient, green and sustainable. You have to follow the route which are the most efficient as well as green and sustainable for the synthesis of that nanomaterial. Unusual physical, chemical, biological properties can emerge in the material at nanoscale. When you go at nanoscale, this is a beauty. Unusual physical, chemical and biological properties emerge at nanometric scale. That's why we are focusing nanometric scale, nanomaterials. Properties may differ in the important way from the properties of bulk, material or single atom or molecules. These are the newly emerging properties may differ from this bulk or individual single atom or molecules. Material properties such as color, hardness, melting point change drastically at this nanoscale. That's why we are focusing on that nanometers, nanometric scale, nanomaterials, nanosystem. Therefore, ultimately, an understanding of this will help us to do the things better with improved efficiency. If you want to improve the efficiency, device performance, you have to go for nanometric scale. Why? Here is the reason. And emerging properties occur at nanometric scale. Now, the lowest limit is 1 nanometer and upper limit is normally 100 nanometers. So, generally talking about that nanoscience, 1 nanometer to 100 nanometers, just a general term. Often, the object with greater than dimension like even 200 nanometers also you can call as a nanomaterials. So why generally people are focusing on 1 to 100, why not 1 to 200, why not 1 to 500? Why people are focusing only on 1 to 100 nanometer range? There are particular some reasons to 1 to 100 nanometer. What are the particular reasons why we are focusing on that? In the range of 1 to 100 nanometer, we observe that quantum phenomena, which is mainly responsible for the changing properties and nanometric scale. So that's why the range 1 to 100 nanometers quantum due to quantum phenomena observed in that range. So is nanoscience is just not related with any small object we cannot say as this nanomaterials. Some properties, new physical phenomena must be occur with that at the nanometric scale, then and then only we can call as nanomaterials or nanoscience implemented or nanotechnology implemented with that material. So here is the main reason, new physical phenomena. Then and then we can call as this material as a nanometric material. Quantum effect are the size and shape dependent. When you go lower and lower size and shape, you will find the effective quantum effect in that material. Quantum phenomena, quantum confinement effect. So what is quantum confinement effect? With respect to change in size, when you reduce the size, the energy level splitting occurs more and more. Energy, the difference between that energy levels increasing when you go lower and lower size, and the band gap of that material increases with decreasing the size, which is generally known as quantum effect. So this effect occurs at a particular size in the nanometric range. It dramatically different from the properties of nanometric scale of the material. So when there is a any quantum confinement effect, the properties of that material is very different, drastically different than the microscale or bulk material. Now, material exhibit remarkable properties, functionality and phenomena in the range of 1 to 100 nanometer. That's why general terms people are using that 1 to 100 nanometer range. These are the some basic reasons why we are focusing in the range of 1 to 100 nanometers. Here is the answer. So you can call 1 to 200 nanometer is also nanometric material or nanomaterials, but particularly a particular range 1 to 100 nanometers. Why? Because this remarkable properties, functionality and different phenomena. Now consider with respect to the surface atoms present and the diameter of that material or that nanometric scale, what we can observe here. The dimension of material or structure approaches the nanometric scale. When you reduce the scale up to nanometric level, the tremendous change occur in the physical and chemical properties take place. Why? Due to this nanometric scale effect on nanomaterials or properties of that nanomaterials. Due to drastic increase of the surface area to volume ratio is the main reason for this enhanced property observed with that nanometric scale. So what happens here? Consider a system having the number of atoms shown in the yellow color and another one is blue color. Blue color we can call as inside or inner atoms, and the yellow color atoms we can call as a surface atoms. So consider a metric system. There are few atoms present on the surface. When you reduce the size and make the different small square of that system, so here is a 1 and here is we have split this into a 4. Now look at here, measure of that part of surface atoms present on the surface. So mainly yellow you can find out here. So yellow atom, so which represents the measure of the atoms present on the surface, and here in blue few are present inside of that. So we are interested only a surface atom. Why? Because these properties are mainly related to surface atom. With more and more surface atom present, more and more effective surface area, and surface to volume ratio is more, and which gives the enhanced properties. Now again you reduce this or cut down this system into a smaller object. So all are atoms present on the surface and in the range of nanometer, around 1 nanometer. Then we can see here the surface area we can find out in terms of kilometric square. That's why number of atoms on the surface increases considerably with decreasing the diameter of that system, diameter of the object or that particle. Properties like melting point, chemical reactivity change dramatically with respect to decreasing the size. So we have to decrease this diameter of that, you will find the effective surface area effective. So that's the surface area to volume ratio increases when you decrease the diameter of that particular material or nanometric scale material. Now, what is area, surface area? Consider the cube of having the length, breadth 1 cm by 1 cm. Also, the 3-dimensional 1 by 1 by 1. So, total surface area 1 by 1 by 1. So, there are 6 faces are present. That's why this total surface area comes to 6 cm square. When you make a smallest block of that cube, particular this cube 1 cm by 1 cm cube, then you will find those small cubes. So consider the total surface area which comes into 60 cm as all of these cubes, smaller cubes having the range of 1 mm. Again you cut down this 1 mm cubes into a smaller particles having the length 1 and having the dimension 1 nanometric scale. You will find the 60 crore centimeter square area, large surface area. That's the beauty. When you cut down the smaller object, you will find the most of the atoms present on the surface, top surface. That's why the total surface area of that material increases tremendously. How you can correlate with this? This cube you can place on the hand easily, but when you make these cubes into smaller part like 1 nanometric square, it covers the most of the football stadium. More than that, you can put an army, around 60,000 army in that football stadium. Now, what happens with particle size and the percent of atoms in bulk or on surface? When you decrease the particle size, you can find out the tremendous increase in the surface atom. Here is the scale. So when in particle size in the range of nanometric scale, like when you go beyond the 30 nanometer, particularly for example, when you go in the range of 0 to 6 nanometer, you will find the most of the atoms present on the surface. So percent of the atoms on the surface is more. Now consider the bulk atom. The bulk atom in a particle size having the range of 30 nanometer is the most of the bulk atoms. When you reduce the size, the number of bulk atoms reduces drastically. So this scale represents the reduction of bulk atoms, and this scale reduction increase in the surface atoms. So we require most of the atom present on the surface, which gives the enhanced property. That's why we are interested in the maximum surface area. Now consider the metric scale and nanometer. What happens with surface area? Consider microscale surface area to volume ratio. In typical example, volume density, consider 10⁻23 atoms present in a cubic centimeter square. So this total number of surface atoms present on that we can call as surface density. So 10⁻15 atoms per centimeter square available on the surface, and others are in the bulk of that. So assume that we have a cube of side a length of 1 centimeter. So we can calculate the total number of atoms. These are for just 1 centimeter. So 10⁻23 into 1 centimeter cube, because we are considering the cube. So total number of atom is 10⁻23. Now consider this surface atom. Total number of surface atom is equal to 10⁻15 atoms per centimeter square into 6 faces, and dimension 1 centimeter square. Surface. So is nearly about 6 into 10⁻15. We can take the ratio of surface to value. So surface to total atoms is 6 into 10⁻15 divided by 10⁻23 here. So this value comes into 6 into 10⁻−8. Now we consider the nanometric scale. What happens with nanometric scale? Nanoscale surface area to volume ratio. So again same example, 10⁻23 atoms per centimeter cube, which is volume density. 10⁻15 atoms per centimeter square, which is the surface density. Consider again the same cube having the side length 1 nanometer. Here is the main difference. In earlier example, we have considered 1 centimeter. Here we have considered 1 nanometer, which is a 10 raised to minus 7 centimeter. So consider the total number of atoms is 20 raised to 23 atom per centimeter cube. Here we have the dimension 10 raised to minus centimeter we have taken here. So comes this around value 100 only. Total number of surface atoms 10 raised to 15 atoms per centimeter cube, having the 6 faces and the dimension here 10 raised to minus 7 centimeter. We are considering surface. Now this value comes into 60. The ratio of surface to volume atoms is 60 by 100 comes into 0.6. So what is the difference between that? The almost 9 times more than as compared with the microscale level. So that's why when you go at nanoscale level, you will find out the nanoscale surface to volume ratio 10 raised to 9 times more than as compared to the microscale. When you consider the layered structure at the atomic scale, consider one cell, single cell, to form a particular small cluster, which is called as magic cluster. You require 13 atoms, and the percent of that atoms is around approximately 92%. So almost all the atoms present on that top surface of that. When you consider the another layer on that particular primary level, say, so there is a 2 cell structure which is a cluster. So total number of atoms is 55. Now there is a much reduction between that surface atom, 76. Some atoms hidden inside that, and if you consider the surface atom total only, so percent is only 76. Again you consider the 3 cells. This is a single cell, double cell, triple cell. Then again there is an increasing number of atoms, 147, but there is a decreasing surface atom. When you go for 1 cell to 7 cell, you will find out that the number of atoms increases, but there is a decrease in the number of atoms on this surface. That's why we require more and more atoms on the surface. So you have to go from 7 cell to 5, 4, 3, like that direction. Now, as to consider the just general example for that nanometric scale, in ancient times, earlier years, long year back, the windows of church, they are showing some pictures having the different colors. But Professor S.G.M from Queensland University of Technology School of Physical and Chemical Sciences said these church windows stained with a gold paint. Gold paint, they are painted by using that gold, which work as a purify the air when they are lit up with the sunlight. What happens with that? You can find out a nice picture on that windows of that church. And here is the range of gold nanoparticles in that ancient times they have used, having the different colors. Having the 25 nanometer which reflect the red color, you can find out some red colors here. 50 nanometer green reflected, you can find some greener portion here, and 100 nanometer the range of that nanoparticle, diameter of, consider that size of that gold nanometer having the range 100 nanometer which reflect the orange color. So these are the not a particular paint, these are the gold nanoparticles they have used in ancient times. Then we can find out the, when you check with the electron microscope like TM, you will find out the sizes which comes in this range 25, 50 and 100 having the different colors. So what happens with that bulk and nano? Why this showing a different colors? By using a simple or single materials. When you light white light incident on that gold, this is a bulk piece of gold. You will find out the golden color or yellowish golden color. Your eye will detect only gold light reflected from that piece of gold. When you consider this nano system, a white light incident on that nanoparticles of gold, you will find a reflected color is red. Why this happens? There is a phenomenon which is called as surface plasma resonance. Here is the positive charges and positive ions core and negatively charged electron revolving around that in atomic scale system or electronic system. These are the responsible for this surface plasma resonance. So when white light is incident on the nanoparticles, you will find out the reflected light is in the red. So what is that SPR? SPR is an resonant oscillations of conduction electron, which electron present in the conduction band at the interface between the negative and positive permittivity material stimulated by incident light. This light, incident light, is stimulated, and that's why we are observing the surface plasma resonance, and due to that surface plasma phenomena, we are getting the reflected color. So nature, there are so many examples which particularly involves in nanomaterials. Like we can consider this feather of peacock having a particular different colors, but these are the colors not any painted or any other. So these are the nanomaterials, nano clusters which reflecting the different colors. So these are some various applications of nanotechnology in sectors of energy, medicine, such as nanotechnology, nano devices, optical engineering, defense for this particular radar and other devices, sensing devices, bioengineering for the medical purpose, cosmetics, nanofabrics for the textile industry. So this field in nanoscience and technology is applicable in various sectors. So we will discuss the remaining part of that introductory part of nanoscience in our next lecture. Okay, thank you.